We can use L'Hopital's rule not just in the 0 divided by 0 indeterminate case, but also if we get the indeterminate of infinity divided by infinity. Here we have two examples of exactly this. The limit as x approaches pi over 2 of secant divided by 1 plus tangent. Now, if we think about both of these functions, the secant function, that's 1 divided by cosine. So it has a horizontal asymptote at pi over 2. Sorry, a vertical asymptote at pi over 2 and minus pi over 2. And it replicates like this, right? It's periodic every 2 pi. But in either case, the cosine value at pi over 2 is 0. So if I try to divide by 0, I have explosive growth right there. I approach positive infinity. So my secant of x function approaches positive infinity. And 1 plus tangent of x, for the same reason, that tangent of x is sine divided by cosine. So as the cosine value approaches 0, that ratio is going to approach positive infinity. So the tangent of x function also approaches positive infinity. So we have the indeterminate form by direct substitution, infinity divided by infinity. We can use L'Hopital's rule to try to recover the limit. L'Hopital's rule states that I should differentiate the numerator. And if you want to derive this yourself by writing secant as 1 over cosine and using a maybe a quotient rule or a chain rule, but either way, the secant of x function differentiates as tangent of x times secant of x. And the denominator, 1 plus tangent of x, again, you can derive that yourself by observing tangent of x is sine divided by cosine, or you can memorize it. The derivative of 1 is 0, and the derivative of tangent is secant squared. Okay, now that we've applied one iteration of L'Hopital's rule, let's try to evaluate the limit, maybe after some algebraic simplification. So we have the limit as x approaches pi over 2. I've got a tangent of x in my numerator, but the secant of x in my numerator is going to cancel with one of those secants. So I'm going to have only one secant in my denominator. And we can further simplify this. Tangent of x is sine divided by cosine. So we are dividing sine of x by cosine of x and by a secant. So we have a sine of x in our numerator, and the cosine times the 1 over cosine is going to give us a 1. Now that we've applied one iteration of L'Hopital's rule, let's try the direct substitution method again. If I try to evaluate sine of x at pi over 2, I have no problem doing this. Sine at pi over 2 is a 1. So we were able to recover a limit, therefore the limit exists and is equal to 1. Let's try this again. The limit as x approaches infinity of natural log of x divided by 2 square root of x. So both of these functions, the natural log is going to approach positive infinity as x goes to positive infinity. 2 times the square root of x is also going to approach positive infinity as x approaches positive infinity. So we have the indeterminate form that we're looking for, and we can try an application of L'Hopital's rule. We will take the limit as x approaches positive infinity. Natural log of x differentiates as 1 over x. And 2 times the square root of x will differentiate as 2 times a 1/2 x to the minus 1/2. So let's clean this up before we take the limit. We have the limit as x approaching positive infinity, 1 over x over a x to the minus 1/2. And with a little bit more algebra, we can say this is 1 over x times x to the minus 1/2, or 1 over x to the 1/2. Now, when we try to directly send x to infinity, The behavior of this function is well known. This term will grow infinitely, while this numerator will stay a constant of 1. So this will approach the value of 0. Right, your denominator is getting bigger and bigger, albeit pretty slowly, but your numerator is a constant. So the value of this function will approach the value of 0. So we were able to get a real number from this limit. After one application of L'Hopital's rule, the limit must be 0.